Hello everyone, welcome to the video presentations of the paper How Bugs Are Fixed, Exposing Bug Fix Pattern with Edits and Nesting Levels. I am Muhammad Shakibul Islam, the first author of the paper. I am a PhD candidate at the University of New Orleans, Louisiana, USA. And you see my advisor Dr. Minhas Faim Gibran in the second picture. So in order to understand the presentation, I will start with developing a background. In the background, we will define three terms, and those terms are abstract syntax tree or AST, bug fix edit, and nested code structure of a bug fix edit. So let's start with the abstract syntax tree or AST. Here is an example of a source code. What do you see in the code? For example, we see an expression inside an if statement, and the if statement is inside a block, and the block is related to a method declarations foo, and the method declarations of foo is inside a class. So this is a hierarchy of code nodes, and this hierarchy in source code can be presented using an abstract syntax tree. In these abstract syntax tree representations of the source code, we see an expression inside an if statement. The if statement is inside a block, and the block is inside a method declaration, and the method declaration is inside a class or type declarations, and the compilation unit is always the root of the AST. Let us assume that to fix a bug, the source code is changed. Here we see that 0 is replaced with 1 to fix the bug. For this study, we need two pieces of information relating to the bug fix change. The number one is what is the change to fix the bug and what the change has occurred. Here we show the ASTs of both pieces of source code. In the second AST, we see the bug fix change is reflected as the number literal, which is red mark is now 1 instead of 0. From the AST difference, we can say that a literal is updated, so it answers our first questions. Now the second question is, where is the locations of the change? If we track the yellow mark labels, we can locate the change. We see that change happen inside an expression. The expression is inside an if statement. The if statement is inside a block. The block is inside a method whose parent is a class, that is type. Thus, finally, we can present the change is in the content of this rectangular box. Now the question is, what is the content of the rectangular box? Here you see a literal is updated. This is the bug fix edit or change, and this answers our first questions that we asked earlier. And second, we call the location of the bug fix edit nested code structure. So this answers our second questions. So at this point, we have defined the terms AST, bug fix edit, and nested code structure of the bug fix edit. Now we'll talk on the motivation of the study. In the earlier studies, researchers tried to detect bug fix edit patterns manually using source code difference. However, manual identification using source code difference of bug fixing edit patterns are time consuming and prone to error. Again, automatic tools are used to compute difference between ASTs, but those tools identify too fine-grained bug fix edit pattern which are often hard to understand by human, and moreover, nested code structure remained absent in those studies. Thus, we asked two research questions to overcome the limitations of the previous studies. The first research question is, what are the common patterns of bug fix edit? And the second research question is, what are the prominent nested code structures that frequently host bug fix edits? This is the novel question that we asked for the first time. To answer the research question, we select 5 software systems and their 4,653 bug revisions. To detect bug fix edit, we use the tool Gumtree Spoon, and to detect nested code structure, we use the tool Gumtree. That's mean for the first research question we use Gumtree Spoon, and for the second research questions we use Gumtree. Note that both the tools output estimate code difference similar to the rectangular box for bug fix changes, which is required for this study. The question is why you have used two different tools for two different research questions is explained in our paper. Now we'll start with the study procedure. For each subject system, we collect the bug fixing commit. Then for each bug fixing commit C, we obtain the nth and previous n-1th revision of the system using the tool JGit. Then using the Gumtree Spoon and Gumtree, we detect difference between the bug fixing revisions and its immediate previous revisions. Collection of such AST differences are then analyzed to detect bug fixing edit patterns and dominant nested code structures of code changes to fix bugs. Now we'll describe how we have processed the AST chains at this step to answer research questions 1. Here we see the output of Gumtree Spoon for the bug fix chains. We see that a literal is updated from 3 to 2, which is the right operand of an expression. From the bug fix chains presented in the bottom rectangle, it is not obvious that the change occurs in an if statement until we see the immediate previous node of the first block node in the nested code structures. Thus, we need to process the whole output to make more sense of the Gumtree response output. That's why we use this algorithm to process the Gumtree response output. We have described the algorithm in the paper. The pattern that we identify using the algorithm are termed as GS pattern in this study. Once we have the GS pattern, we aim to identify whether those GS patterns match with any of the bug fixing edit patterns defined by Pan et al. The study of Pan et al. Has identified the highest number of bug fixing edit patterns in a single study before this study. Moreover, according to the number of citations, this is one of the most important papers on bug fixing edit pattern. Thus, it becomes a benchmark for the studies related to bug fixing edit patterns. In the rest of the presentations, we use the term pan pattern to refer a pattern identified by Pan et al. We also verify whether Gumtree Spoon is able to identify any new bug fixing edit pattern as opposed to the pan patterns in our dataset. In this table, we present the pan patterns identified in our dataset. We are able to detect 21 types of pan pattern distributed in 7 categories as presented in the table. The method declaration category contains the highest number of bug fixing changes, followed by the if, method call, and class field categories. Noticeable that the first 4 categories consist of almost 90% of all bug fixing changes. Category Swiss experiences the lowest number of bug fixing changes, preceded by the assignment, loop, and try categories. In this table, we present the new patterns identified in our dataset. We identify 70 types of new bug fixing edit patterns distributed in 11 categories that are presented in this table. Although some of those 17 bug fixing edit patterns are already identified in different studies, except the studies of Pan et al., we identified completely 4 new bug fixing edit patterns. While some of those patterns can be easily understood from their names, such as addition or deletions of a method call, other patterns are defined in the paper with example. Now we see the local variable consists of the highest number of bug fixing changes, followed by the categories of method call, return statement, and assignments. Again, those 4 categories consist of almost 90% of newly identified bug fixing changes. Now, the pattern local variable implementation experiences the highest number of bug fixing changes, followed by the pattern local variable additions. The patterns return implementations and assignment addition deletion experience almost equal amount of bug fixing changes, and that is almost 13%. Next 3 patterns method called target chains, method called addition, and method called deletions experiences 10.9.8%, 10.50%, and 7.23% of bug fixing changes, respectively. Those seven patterns together contribute almost 84% of bug fixing changes. Now we will describe what we have done to answer research questions too. Actually, we will elaborate these steps or action that we carry out to identify nested code structures patterns. Here we go. At first, we identify the sequential nesting pattern of the nested code structure using MGFSM algorithm. Then we identify the cluster of the patterns. Thus, clustering provides a convenient way to characterize and label the identified nesting patterns manually by experts. Finally, we manually label the identified nesting patterns. Let's dig further into these steps by starting with this one, sequential pattern. As mentioned earlier, we have used MGFSM algorithm to identify sequential pattern mining. You will find a detailed description of the algorithm in the link given here. To run the algorithm, we apply three constraints that include maximal pattern, no gap between two successive nodes. A pattern must have at least 1000 occurrences. After running the algorithm, we have found 385 nesting pattern types that we use for clustering in the next step. Let's look into the details of this clustering step. To cluster nesting patterns, we use K-meter's algorithm, that is a variant of K-means. To determine the optimal number of cluster, that is K in K-meters, we use gap statistics method over the available options such as elbow method. We use the longest common subsequence based string metric to measure the distance between a pair of mine nesting patterns. We define the distinct functions for any two mine nesting patterns S1 and S2. Here S1 and S2 are two finite sequence of nodes, that is nested code structures, and this is the length of the longest common subsequence between S1 and S2, and this one is the length of the longest sequence between S1 and S2. Using the package Python string similarity, we compute the LCS metric values. Then to cluster nesting patterns, we run the open source implementations of K-meter's algorithm implemented in the package PyCluster 1.49. At this stage, we have 10 clusters of nesting patterns. After having the clusters of the patterns, we manually label each member of the clusters. For manually analysis, we divide the source code nodes in two sets. The first one is low-level nodes, and the second one is high-level nodes. Each author aims to identify if a low-level node in L is contained in a high-level node from each. For example, here we see a low-level node return is located inside an if block. Then the authors label the hierarchy as return block inside an if block. If a high-level node block H1 is containing another high-level node block H2, then the pattern is categorized as compound and represented as H1 block inside another H2 block. Finally, we identify 37 types of nested code structures patterns divided in 6 categories. There are 9 types of nesting patterns belong to the if category that represents the largest amount of total number of patterns flowed by the compound category that consists of 15 types of patterns contribute to 31.82% of the total number of patterns. The categories try-catch and loop contribute to 9.89% and 8.02% of total patterns respectively, followed by the chain method invocation category that consists of 5.93% of total patterns. The number of patterns belong to the synchronized category is the lowest, and that is 3.6% of the total number of patterns. By inspecting individual clusters, we find some interesting patterns that cannot be identified without considering hierarchies of nested code structures. For example, if you see the 23rd clusters, that is a block inside And the loop block is the most bug-prone pattern as it experiences the highest number of bug fix changes, followed by the first cluster if block inside another if block, which is slightly lower than the former cluster. It is very interesting that throw blocks inside if blocks are more bug prone than throw blocks inside try catch blocks. Although in the edit patterns we see that the number of changes in the category try is very low, the opposite result is observed here, where category related to try catch experiences the second highest bug fix changes among the categories of simple high level nodes. It means that pieces of code inside try catch frequently experience bug fix changes. A similar observation is also applicable to the synchronized category. Surprisingly, only 5 clusters among the 37 clusters contain tree-level containments, and the clusters are 28, 31st, 33rd, 36th, and 37th. All these tree-level clusters consist of only 3.64% of all patterns, and no pattern is found that contains more than 3 levels of containment. So here's the end of our second research questions answer. Now we'll talk about the limitations of this study. First of all, the size of the dataset is small, although we have used 5 software systems. The second, the tool that we have used in this study have some limitations that can impact our findings. And the third one is the human ratings of the nesting patterns are subject to human errors, right? Although we have measured agreement between raters. So here is the summary of the presentations of the paper. In this study, you have reported 38 patterns, which is the highest number of bug fixing edit patterns reported in a single study. Among those 38 patterns, 4 patterns are completely new. And moreover, we have also exposed 37 new nesting patterns of bug fixing. The future work, we need to conduct a study with a large dataset to identify more unknown bug fix pattern. And we need to focus on a specific bug or issue types such as security bugs or performance issues. Thank you. This is the end of the presentations. If you have any questions, you can send me an email or you can post your questions of the comment sections of the video URL. Thank you.